Hey guys, it's your host, Subhra. Welcome to your favorite channel, Subhra the Geek. So today we are going to be talking about another video of our statistics series, Linear Models Part 2. So today Debayan will be introducing new concepts, and these two videos, guys, I'm telling you again and again a lot of times that Linear Models Part 1 and Linear Models Part 2 are very important. These are the things from which when you go for a data science interview, they are always asked questions. So guys, if you face any problem during the course of your journey, we have our exclusive Discord server ready and linked down below, where I and Debayan will be always there to help you out. Guys, if you have any suggestions, do comment in the comment box down below. And if you want to support us, these videos are made like without any benefit for us. So if you want to support us and if you want to help us, please share it with all those who needs this kinds of stuff. So guys, without further ado, I am your host Subhra. Along with me is
Debayan.
let's start, shall we? So Debayan, in the last video we learned about the equation or the linear form of linear models. So
Mhm.
what are we gonna learn today? What is the new things we are gonna learn, and which will help our audience especially to crack the sexiest job of 21st century?
So today we're going to learn something that's frequently asked in interviews, which is when do you use a linear model, right? What conditions must the data satisfy or your experimentation satisfy? So you can start using or thinking about linear models, right? So we're going to learn about all those conditions. Very important, must note it down. Um, and then we're going to talk about how does the coefficients of the linear model come into play, and how do we use discrete variables over there, right? So discrete variables are by definition not continuous, so how do we use them in a continuous kind of model where like all the variables are generally considered to be continuous? So that's what we have for today.
So guys, we got a brief idea about what we are gonna learn today, and now Debayan will be moving to his tab and he'll be explaining each and everything in minute details as he does every day. So thank him in the comment section as much as you can for his effort and hard work. Without further ado, let's move to his tab and let's start. So Debayan, would you start sharing your thoughts and start explaining?
Mm-hmm. So in the last video, we left off at the general form of the least squares line. For those catching up from there, let's have a let's quickly write it down so that it's there for our reference. So this is the predicted value of y, and this can be the simplest form of the ordinary least squares equation. The linear model looks like this, right? So this is your input variable, right? This is what you know. This is independent variable. This is what you know, and this is the prediction, right? So what we didn't explain in the last video, which we're gonna explain right now, which is what are these two, right? These are what you would call the coefficients of regression, right? These are the coefficients which determine how strongly your input variable is gonna affect the prediction, right? So beta one is what determines the strength of X or strength. When I say strength, do not take it literally as in some kind of strength metric, but think it of as it's how much influence. So this is the question that beta one answers over. How much influence does X have on the prediction?
So guys, to give you a joking manner, it's like
Mhm.
you don't take the weight of Thor, but you take the weight of Thor as a king after Odin.
So, yeah, nice. Uh, okay, coming back from that lame joke. Uh, beta one, beta two, beta one, beta zero. So beta one, what beta one answers is how much influence does X, that specific variable, have on the prediction, right? but on beta 0 you don't see anyone, right? So this is what you'd call the default variable of the prediction when none of the variables or none of the input variable is given, right? So if x is 0, then y is equal to beta 0, right? Because that influence is not there, right? If beta 1 is 0, that means no matter what value of x you give, it still does not influence the value of y, so y is still equal to beta 0, right? This is in textbooks you will find this is called the intercept, right? And this is called the y-intercept because it's for y. But remember, what the intercept means is this is the default value of the prediction when nothing is given, when you have no input predictions at all. So this is the base limit of y cap, or what the prediction says. How do you can you estimate the value of beta 1 and beta 0? Obviously you can. Normal or the standardized ways of computing these two variables is what encompasses machine learning and deep learning as a whole, right? So the whole industry rests on these equations. You better learn this very well. um, so obviously you can use gradient descent if you've heard of those terms into estimating these two parameters. But just for quick maths, if you were to say the slope beta 0, beta 1, you can approximate it like this. So it's like standard deviation of y divided by standard deviation of x, right, whole into r, where r is the correlation between x and y, between the input and the output variables, right? So beta 1, you can approximate the value of r using quick maths like this, and sigma y from the data points of the data set, you can approximate sigma, the standard deviation of y, its standard deviation of your input variable, and from there you can get, and the correlation as well, you can get the beta 1 approximation directly, right? And beta 0, well, that's pretty obvious. If you have the data set, you just change your subject and you get it like this. So right, this is a very good approximation of beta 0, the intercept. Now so this y cap and sorry, y bar and x bar, these are not predictions, these are what you'd call mean, right? This is mean. So this is what you'd call this is called the sample mean and sample of these two variables. So x bar and y bar are the sample mean, not the population mean, not the true mean, but the sample mean given a subset you have taken of the population of x and y, right? So here's another nice trick. The least squares line of this equation will always pass. So y cap is equal to beta 0 plus beta 1. This equation will always pass to x bar, y bar. It always has to, right? And this allows you to quickly approximate the slope as well. And so the variables that you can approximate directly from the data set, right? So you can approximate these two directly, right? You can if you have the data set, you can approximate these two directly and this as well. So approximately, like just from looking at the data set, you can approximate slope, you can approximate the intercept, and you can get all the properties of the standard form of the linear equation. And this extends to as many variables or input variables as you want. So it can be beta 1 x1, beta 2 x2, and so long and so forth. Now, moving on to the next section of the lecture. So when you go for a data science interview, or when you go for a normal interview where you have to work with data analytics, like munching with data, doing stuff on Excel, or even Excel, stat and all the stuff, they will ask you very simple questions regarding linear models, because linear models are so powerful in how they work, and 99% of the cases a linear model will do the job just fine, right? So some of the questions, one of the major recurring questions that they ask is, when do you use a linear model? Right? You have a set of data points. When do you choose to not use a linear model? When do you choose to use a linear model? And from there, how do you understand when is gonna linear model be powerful enough to solve the problem that they're asking for? Right? You understand the normal ordinary least squares form, right? You understand what it means to see this form, right? You understand what it means. It's simply the influence of the input variable on the predicted variable. That's what it all means, right? But when do you use such a model? When do you use such a tool, right? We have three conditions that you must remember. That's just three only, nothing more, nothing less, right? Condition number one, it's called linearity. You need to have some form of linearity in the data, right? What do you mean? Right? I mean that the relationship between your input variables, please mind that I say that it's input variables, not input variable. I'm talking about multiple variables at the same time, so you must check the correlation effectively, or the pattern, or the graph separately for each of them. Variables versus the predicted variable or the target variable, whatever it is. You must have an assurance, or at least see that the relationship between the input variables and the predicted variable or the target variable should be linear in some manner. That means if the input variable increase, the predicted variable either increase or decrease, right? So there is some form of linearity in how they behave with respect to each other, right? And it is possible to fit a linear model to a non-linear data set where this relationship is not conserved. It's not linear, but it becomes a little bit difficult. It becomes problem to have a good model fit on the data set. Your predictions might not be all the well good, right? That's why when you use if you're using into machine learning and you're using linear regression, for instance, on your model, you might see it performs very well. You have an accuracy of 77%, while a normal non-linear model, or a non-parametric model like SVM or random forest might give you better results, right? If you do not understand those terminology, that's okay, but I still want to give you an example that it is possible to fit non-linear data with linear models, but know that it's going to be problematic. It's going to be not capturing the essence of the data set. So you should know those limitations, and that depends on whether the input variables and the predicted variable are linear in their relationship. So how do you know whether they're linear? Just use a scatter plot or a residual plot, right? If you do not know what a residual plot is, please check our previous video. If you do not know what a scatter plot is, please check our, I believe, Subhra will link it. Subhra will link it in this video at this timestamp. So
Yeah, yeah,
please have a look at those videos to understand how do you see the plot or the relationship, and understand what it means to have a linear relationship. The second important condition that you must look out for is nearly normal residuals. Let me write it down. Nearly normal. Doesn't have to be exactly normal. If it's exactly normal, you know what you're dealing with. It's very easy to work with, but it is never almost the case in the real world. So it's nearly normal residuals, right? So your errors, residuals are your errors from your prediction. So if your model predicts that y is equal to 5, but the reality is the y should be is equal to 7. So 2, that gap between the predicted and the observed is 2. That is called the residual, right? And if you calculate or the compute the residuals for all the prediction in your test data set or your validation data set, and you plot them just to see what the data distribution looks like. Do a histogram. That's what I mean. Do a histogram of the residuals of all the errors that you get from your test data set. If you see it normally distributed, that means the relationship is linear, and you can actually work with that with a linear model on that data set, right? So the idea is your residuals histogram should be nearly normal, nearly normally distributed. I'm keeping it loosely coupled over here, nearly normal. It looks normal, that's okay. And when I say normal, I mean it looks like a bell curve or nearly close to a bell curve. Then you're good, right? And if it should be centered around zero, like that. That's what we mean. It should be centered around zero if possible, right? Now if there are unusual observations which do not follow the trend of the data, think of like maybe the Swiss roll data set in NSK-Learn, if you heard of those. On the moon data set, clumps of clusters of data here and there with nothing but space between them. Those are unusual observations that do not follow normal linear trends. So you cannot satisfy normal residuals in those scenarios, right? So linear non-linear relationships are really hard to model using a linear model. So this is what proves it, right? So non-linearity can be a problem, is the problem, right? Non-linearity in residuals can be a problem. can be an issue, right? So how do you check the normality of the residual? Just do a histogram, like I said, and just like, get the residual values, get the area of all those variables, just plot the histogram. That's it. Or if you want to do, if you know what a KD is, or kernel density estimation graph, right? You can get it in pandas if you're using Python. Just do plot type KD, right? And you should get something that looks like this, right? Or a histogram that looks somewhat like this, somewhat close to the bell curve. That's all what you need to confirm where this condition is satisfied or not from the data set. So that's the second condition. And what's the third condition? It's called constant variability of the data, right? So let me write it down. Constant variability of the data. When I say variability, I mean in the same terms as a variance from where standard deviation comes, right? So square of the standard deviation is variance, right? So we must have constant variance throughout the data set. So what does it look like? What do you mean when you say a constant variability, right? So if your data points is something that looks like this, right, and your least squares line is something like this is the x, this is y, this is your OLS, or the least squares line, ordinary least squares line. If your data set are like equidistant from each other, or like sort of balanced on either side of your line, that's a very good cue that you have constant variability around your OLS line, right? And what does it mean? What does it mean? It means that the variability of the residuals in the previous point around zero should be roughly constant as well, right? If this is true, then this should also be true. I will give you some time to think about that, but keep note in mind that if your variability is constant along all along the line, it's sort of scattered evenly across on either side of the line. That implies constant variability. That's all you need to know, right? This condition also has a very special name. Interviewers will ask you about this, and people almost forget. It's called uh, homoscedasticity. Let me skedasticity. Did you guys can see that? Okay, let me write it again. Homoscedasticity. Homoscedasticity. This is the name of this condition that we are talking about, right? And how do we check for variability? Just look at the previous point, the residuals plot. And if you don't understand, if you can't figure it out, if you can't plot it, just plot the data set, plot your OLS line, and see how it looks like the data set, how the data points are distributed along both sides of the line. If it's evenly distributed, you have constant variability. And only when you have these three conditions fulfilled, right, they sort of all depend on each other. If one is true or two is true, automatically the third one should be true, right? If all of them are satisfied, only then you can think about using a linear model in your data set. In this section, we're going to talk about an important thing, I think, which many people do the right thing, but they do not understand why they do that thing. And what I'm talking about is when, like, if you have some experience working with, in Python or R, right? So what you do is that if you find a discrete variable in your data set, before feeding it to your machine learning model or to your statistical model, what you generally have been told to do is to convert your discrete variables or categorical variables into one hot encoded variables, right? You must have heard of this. In pandas we call pd.get dummies. There is a function on that. And why do you do this, right? Before we proceed, if you do not know what a categorical variable is, Shubhra will link it over there. So in the beginning of this video series, please have a look at it and then get back over here when you understand that concept. So how do you work with that, right? So in it's a linear model, right? Looks like something like this. Again, just for your convenience, I'm writing it over here, right? So generally, this is generally a continuous variable, right? This is continuous, right? So these are obviously real numbers, so these are also continuous as well. They have to be. They are what determine the strength or the influence of the input variable x, or x1, x2, how many variables you have, on the predicted variable y cap, right? So these are obviously continuous. But x can be continuous generally most of the times in a linear model. How do you use discrete variable over here, right? Let me give you some context. Let me give you what I'm trying to ask over here. Let's say your blood group is, let's say X is equal to blood group. There are six or seven, six, right? Subhra, how many blood groups are there? Six.
A, B, A, B, all 8, I think.
Okay, yeah, I'm not human, so I forgot. Humans with group set. Uh, so there are, as Subhra says, there are eight blood groups, right? So how do you use the fact that someone has a blood group of AB positive, right? And how do you use that in your model, right? It doesn't make sense to give it a continuous value. So what do you use? You might say, okay, I'm gonna encode it, right? So you're gonna say that O positive is 0, O negative is 1, and A positive is 2, and so on and so forth. You can do this kind of encoding, right? And then you're gonna use this number in place of X. You could do that, right? But you're generally told not to do that, right? Why do you think that happens? First of all, you must understand that when you put some kind of variable in the model, right? The model has no conception of what that variable means. It's just a mathematical tool. The model has no awareness of what it means or what it means to you as a programmer, as a data scientist, as an analyst, right? So you must make it explicitly clear that it has some specific meaning in the way you define it, in the way you give it values, right? So giving it values, this does not look any different from any other continuous variable. It will not think of it anything different, right? So what you instead do is make it explicit in this way. You ask the question, is it O positive? Is it O negative? And so on and so forth, right? It does not depend on whether the blood group variable is X or not. Like, it does not matter on that part. It matters what does the variable mean, right? Each of those classes are generally mutually exclusive for every sample, right? If you have a one single person's worth of data, you're going to put that data into your model. If that person is A positive or B positive, it doesn't matter what the other values are, because it's mutually exclusive. It has to be that, and everything else has to be no, right? That's what it means. So one hot encoding allows you to convert that concept into ones or zeros, right? If your X is 0, right? If your X is 0, it has no influence effectively. If your X is 1, yes, it has some influence, and that influence is determined by your coefficient over here, or by your influence in variable over here, your slope over here, right? Now why 1? You can say it's also like this, right? It's also another variable, but one is what you'd call an idempotent variable. It doesn't matter what you multiply one with, it does not change that number. Basic 101 maths, right? So one does not change any other number. It's immutable. It doesn't change anything. So when you say is it O positive, if it is true, then add that influence, add that factor that it is true, and everything else is zero automatically, right? That's why you convert your blood group into, if there are eight blood groups, you convert it into an 8-bit number. This would mean that it's O positive. This would mean that it's O negative. What it means is that this position tells you what it means, right? And this is mutually exclusive. When this is one, everything else is zero. Only that influencing coefficient will influence the predicted variable. Everything else will not exist at all in that instance. So this is why, or this is how I answered both of them in the same way, right? So this is why and how you use a categorical variable in a linear model. Now, the last part of this video, we're going to talk about outliers, right? And outliers is a pretty subjective topic. If I'm being honest, like in the real world data, it's very difficult, or it's not always clear as black and white what can be an outlier, what can be abnormal with respect to the data that you see. But this has important in like impacts in in places like credit risk analysis, or or anomaly detection, for example, in live or batch kind of systems, where you have to detect something's out of place or something's really unusual happening in real time, right? So the very definition of outliers is that they are rare. You can't find them happening all the time, so you really can't train a model like that. right? But what is interesting about an outlier, and that is one of the important concepts behind denoise in autoencoders, if you're reading into that, or even anomaly detection models, is that the very fact that they are abnormal, they do not occur and in very frequently, and they're rare by definition, is the way that we find them, right? Have a look at this first plot over here, this scatter plot, right? So you can see the normal data is over here, right? That's all good. You have the OLS line drawn over here. This lone point over here, just to make it more clear, this lone point over is totally separated from the cluster, and that is what makes it an outlier, because it does not follow the trend of the data, right? It's too far away from the cluster. It does not look like a part of the cluster, right? Look at the other one. So this one is the data, right? So if you're drawing a linear model, so it will look like something like this, for example. But that point over there is totally separated from the pack, so to speak, and that is it's very visually unique that it's an outlier, right? If you're talking about a box plot, if you do not know what a box plot is, Shubhra will link it in this video at this timestamp. Please have a look at it. It's not as like it's not easy to understand it quickly at glance, but please have a look at it and then come back to this video. So over here you can see that the box plot, the so this is the mean over here. You can find the quartile ranges at the end, the 0th quartile and the 100th quartile over there. So these are the 0th quartile and the 100th quartile over there. You can see the range, and then what you see over here is an outlier. This is an outlier, and this is completely separated away from the data point. So that corresponding histogram of that value, right, or the cumulative histogram will look something like this. This is the normal distribution. This almost looks like a normal distribution, right? But suddenly you have some one point over here that is totally away from the normal, far away from the normal. If the normal is over here, it's far away from here, right? Just to emphasize the distance over here. If this is the normal is over here, normal is over here, it's far away from there, and that is what qualifies to make it, like, you can call it an outlier. And the very fact they're rare, the very fact they are totally outside the domain of the value range, or the possible value range of the normal data, is the reason how you can define, or you can basically define what you mean by an outlier. And this is one of the easiest ways you can detect it, or you can define what an outlier can be in your data set, in your context, in your domain, or in your problem statement.
So, Debayan, I feel that's all for the day.
Mm-hmm.
And thank you for explaining a lot of things, starting with regression, then how to use a linear model, then what are the things we need to check, when to use a linear model. Uh, then we talked about one hot encoding, and finally outliers. So I think our audience will get a lot of understanding, and they will be ready for the industry and ready for interviews. So, guys, if you want to support us for this free kind of stuff, please do share the content. Please subscribe to our channel. Please hit the like button if you like the video. It will help us a lot. And, guys, that's all for the day. If you face any problem during the course of your journey, we have our exclusive Discord server ready down below. The link is given down below. You can follow us over there. You can hit me up with a comment, and we can talk through it, and we can try to solve your problem. So guys, don't worry, we are always there with you. So without further ado, that was all for the day. I was your host Shubhra, and with me was
Debayan.
signing off. Bye bye.